there's electrolysis. So a bulk of what I'm going to do, or a big chunk of what I'm going to do is electrolysis. But I'm going to try and cover as much of the redox topic as I can in the time we've got today. Remember, the redox topic would have taken you a number of weeks to do. So this is a fly through it, picking out the most important bits. It's really important that you, by doing past papers, full past papers or questions from, say, Physics and Maths Tutor or Educate on this topic, practice what you're doing. Personally, if it was me, having done this today, I would go to Educate and can I do a bunch of questions just on redox? And it's all within what they call the chemical changes topic, which includes acids as well, which we did last week. Loads of those before then doing some Physics and Maths Tutor questions on it, before then doing past papers on this topic. All right? So redox. Redox is essentially it's two words combined together. It's reduction and oxidation. Right? It's oxidation and reduction. You can't do one without the other. Reduction and oxidation, the definition more important than any other you need to know for it is oil rig. Oxidation is loss of electrons. And reduction is gain of electrons. And you're often asked in just about every exam paper, what do we mean by, or which one of these things is oxidized, which one's reduced? And you would say, well, it's the one that's lost 2 electrons or gained 3 electrons or whatever. Really common questions. But there are other definitions of redox. There's 2 more you learn at GCSE, which correspond to the organic topic more than any other. So oxidation is also gain of oxygen. An example might be carbon turning into carbon dioxide is gaining oxygen, right? Or methane reacting with oxygen gives you carbon dioxide, so carbon's being oxidized, so it is gain of oxygen. And reduction is loss of oxygen, which you sometimes will see, and I'll give you an example of that in a minute, if you don't mind, to see the example in a second. And there's another definition which you would really not see that much at GCSE, but it can also be loss of hydrogen and loss of hydrogen over here and gain of hydrogen over here, but you're not really going to see that. The only time you see that in chemistry really is here if it's gain of hydrogen. Gain of hydrogen. The time you've seen that possibly is in your organic chemistry, those of you doing triple, where you've got an ethene reacting with hydrogen to give ethane. That's an example of reduction as well. But essentially, most importantly, the definition at the top there is what you want to know. Right, so what do we cover in the redox topic though? The first thing really is displacement reactions. The displacement reactions you do right back at key stage 3, and you know these are reactions where one element displaces another from a compound, right? And your classic example, the one that you've seen and done a bunch of times, will be this example. It might not be the one you get in an exam, but it's the most likely one you're going to get in an exam, where you take iron oxide, which is a compound because it's made of 2 different elements combined together, and the element carbon, and you heat them together. This is the way of extracting extracting iron from its ore, which we call smelting, by the way, or heating with carbon. And if you balance that, it looks like that. Okay? So the carbon has turned into carbon dioxide. So the carbon's gained oxygen there. So it's oxidation and reduction. 3, 2, 1. 3, 2, 1. Oxidation is gaining oxygen. Must be losing electrons, therefore, right? And iron is losing oxygen, so that must be reduction, right? So you can't get one without the other, and that fits with this example here. This is displacement because carbon is displacing iron from the compound, right? So carbon's being oxidized, iron's being reduced. And that shows then, doesn't it, in displacement reaction that carbon is more reactive than iron. Okay, carbon is more reactive than iron, so you can displace iron in this way, just like the old Minecraft days that you guys were addicted to back in the day. You could displace iron, you could make iron from iron ore by heating with carbon, and that worked. It worked nicely. If you try that with aluminium, though, it doesn't work. Okay. With aluminium, you'll find that aluminium is more reactive than carbon, so that reaction not possible. So that's what makes aluminium very expensive. It's not that it's not a plentiful ore, it's just that you can't extract it by simply heating with carbon. So not possible to extract Al from Al2O3 because aluminium is more reactive Sorry, my writing has gone really haywire. Aluminium is more reactive than carbon, right? Aluminium is more reactive than carbon, so you can't do that equivalent reaction. This smelting only works with copper and iron, elements that are less reactive than carbon. So then you have to use the more powerful method of extraction. And I like that word powerful, that's why we do it. So the powerful method of extraction is electrolysis. We can use electrolysis to extract any metal from its ore because it's such a powerful technique. I'm trying to sharpen a pencil. Right, so aluminium can be extracted from ore using electrolysis. Electrolysis by definition is splitting. Lysis means splitting, splitting a compound into elements. Using electricity. Right? And I'm going to come back to that in a bit of detail in a second, I think. I think what I'll do to start with, I want to show you some... No, we'll come back to that. That's all right. We'll do tiny bit more, and then we'll do some exam questions together, okay? So we can extract aluminium from the ore using electrolysis. By the way, with electrolysis being so powerful, you can do electrolysis on iron oxide, you can do electrolysis on copper oxide, but we don't industrially because this process, this powerful method, is expensive. And the expensive bit is probably not where you're going to get the mark. The issue is to do really with the fact that it requires lots of energy. And that has cost implications, right? But it also has implications in terms of generating carbon dioxide when you make that electricity, so it's potential global warming issues and so on, right? So, moving on, I realise I've done that fairly quickly, but we're going to look at electrolysis of aluminium a bit more, because that's if I had to put a pound bet on what's going to come up in this exam, I haven't seen the aluminium oxide questions for a bit. Right, so electrolysis of aluminium oxide is a very specific piece of information that you need to know. Aluminium oxide or bauxite is a very common ore. Making aluminium from it is hard to do because you have to do electrolysis on it, and electrolysis requires the compounds to be molten or aqueous. Are we okay at the back? We've got a question. I'll just pause this. If you've got a question, I'll deal with it. Right. So electrolysis has to be done with the compound must be either molten or dissolved in water. So it's only done on ionic compounds, and I haven't done a session on bonding yet. I mean, I'm spending time on bonding with my classes this week and next week, and I'm sure you'll be too. But remember that electrolysis is only on ionic compounds. And for them to conduct electricity, they must be either molten, which is another word for liquid, or dissolved in water, which we call aqueous. Otherwise, the ions can't flow, and this whole process doesn't work, right? So the problem you've got with aluminium oxide is it's got an insanely high melting point. And so you have to, the reason that aluminium oxide was, or aluminium rather, was so expensive back when they first developed the technique for making it, was that you had to melt aluminium oxide, and I don't know the number, but I guess that aluminium oxide is in the thousands of degrees C melting point. So, and lots of people tend to remember this, it sticks in people's heads. So aluminium oxide is dissolved in something called cryolite, which I think is spelt like that, to reduce its melting point. And it's kind of a dissolving in this substance, cryolite. And I just use this as an opportunity to remind you of some topic 1 stuff. It's a mixture, right? Mixtures have lower melting points than pure substances. So that fits with what you've been taught elsewhere, and an opportunity to remind you of the key points. Mixtures have a lower melting points. Melting points. And you learn that with ice. You chuck salt on ice. Come in. Find a chair for maybe outside if there's none in here. So mixtures have a lower melting point. And so we reduce the melting point of aluminium oxide by mixing it or dissolving it in cryolite. So you need to know a little bit about that. But let's just write out the reaction. This could be for any ionic compound. If you do electrolysis on it, this is what happens. So I'm going to do a bunch of these. So I'm going to do sodium chloride, aluminium oxide, which is the one we're just talking about, or something like, I don't know, let's do lithium oxide. If you do electrolysis of a molten compound, an ionic compound, you will get the elements. So look out for this, because you need to make sure you know the formula of the elements, which are Na. The metal is always just written as the metal on its own. But in just about all cases I can think of, at least, is the other substance, the non-metal, and the ones that you're likely to get are diatomic. So you have to be a little bit careful with balancing the equations. So to balance this top equation, I'm not going to teach you balancing equations today, but you might have to do some work to balance those equations in your exams. These are all liquids, so they have to be heated up, melted, and at those temperatures, these metals will always be liquids as well, and the non-metals will always be gases. So look how similar they are to each other. So I think what we'll do is we'll move on now to talk about what's going on in electrolysis generally, and then we'll come back to aluminium oxide. But I thought it might be nice to do, the whole point of these sessions is to do some exam questions. I thought we'll have a little go at that, and then we'll come back to aluminium oxide and other types of electrolysis. So this first question here, I'm going to do some ionic equation bits a bit later on. But if I give you the help by showing you that this is simply magnesium displacing zinc, what you'll end up with is those electrons are swapping from the magnesium to the zinc, right? So including state symbols, AQ, and solid, right? So I'm not too worried about that bit for now. But the thing I wanted to think about is question 6.4 for a second. So how do we know it's both oxidation and reduction going on there? How do we answer that question? Tell each other briefly. I won't name names, but I got a good but not perfect answer from someone in the room. So you're right that magnesium is losing electrons and zinc gains electrons. Put your thumb up if you got that bit. Most of you did. I could hear that around the room. But why not tell the examiner everything we know? Magnesium's losing how many electrons? 2. So let's say that then. Sometimes I've seen it where you have to say that as well. In fact, I think in one of your mocks it had that. How many is zinc gaining? 2. Or zinc, it should say zinc 2 plus is gaining 2, shouldn't I, really? Right, so that would be all you have to do for that. And so this one is, oxidation is loss, so that's oxidation. And this one is reduction. Which is the more reactive element here, magnesium or zinc? Shout out in 3, 2, 1. Magnesium, yeah, because one's displaced the other. Right, so next question is about electrolysis of aluminium oxide. So aluminium is produced by taking a molten mixture of aluminium oxide and cryolite. We've just done that. Why do we use this mixture as instead of just pure aluminium oxide? Discuss that briefly. Go. So the answer is, the whole point of the cryolite is to reduce the melting point, right? And that's that mixture. Mixtures reduce the melting point. So it's just practicing what we just did. It's just seeing it in an exam format. And that's only worth 1 mark, right? Reduces the melting point. The reason for doing that is to, I heard some of you say it, but not all of you. The reason for doing that is to allow the ions to flow. So it allows for it to conduct electricity. So it can conduct electricity. Without the ions being able to flow, without those bonds being broken, ionic bonds, it can't conduct, ions can't flow, the aluminium ions can't go to the cathode and do what they need to do. So, and we're going to do 7.3 briefly now. It's the balanced equation here. We just talked about that. The formula of aluminium oxide is further, well, I've just told you that, it's aluminium oxide. We're not going to work out that now. I'll tell you briefly why. Aluminium is 3 plus, and oxide ions are 2 minus. So to have an even number of charges, so you've got 6 pluses and 6 minuses, so that's aluminium oxide. Oh, this is a half equation. Oh, I messed up. Ignore what I just said there. Forget that. Right. Okay, so let's do a little bit on electrolysis and we'll come back to half equations. We'll come back to aluminium oxide specifically. So in electrolysis, what we've got is a pot, right? And in that pot, we've dipped 2 electrodes, and those electrodes are usually made out of graphite, but not always. And we've got a power supply unit. Looks like that. And then the substance there, the liquid, whether it's a molten ionic compound or later we'll talk about aqueous ionic compounds, we call that the electrolyte, and be expected to know that. The ions are the electrolytes, okay? Remember, this only applies to ionic compounds, and so it's ions that are present. And I'm going to use sodium chloride as my example to start with. In fact, I'll do aluminium oxide, shall I? Since we're talking about that a bit, because I've got a funny feeling that's going to come up. So we've got aluminium ions, we've got oxide ions that are floating around in that pot, and they're free to move because the ionic bonds have been broken. We've got a power supply unit, and usually that's labelled for you, but the long line represents the positive electrode, and the short line represents the negative electrode. So chemistry is always about electrostatics, and the negative ions will go to the positive electrode because they're attracted to it, because they've got an electrostatic attraction to it. And the positive goes to negative, negative goes to positive. Okay, so this is the bit I found looking at your mocks, not just my classes but all classes. This is where people get muddled. Okay, so once you've sort of copied that, I want you to put your pens down and we're going to discuss and think and talk about it, because this is where you're getting confused. If you're copying, you'll struggle. Right, so in the pot we've got ionic compound has been melted. So instead of being an ionic lattice like a solid would be, like this lattice here, we've got oppositely charged ions in a 3-dimensional structure with the ions held in place. We've melted it. So we've got green and grey blobs, aluminium and oxide ions moving around freely. And as I said, chemistry is all about electrostatics, and it's all about the fact that the ions go to the oppositely charged electrode. And that's all being persuaded to happen or forced to happen by the power of the power supply unit, right? Or the electricity, if you like. So aluminium ions are going there. Now, what you get muddled up with and confused about is you kind of think that's the end of the story. Or perhaps you think it's aluminium going to the ion. But the chemistry happens on the surface of the electrode. This is where the exciting bit, if you're a chemist, happens. So on the surface of the electrode, the aluminium ions gain electrons. Now, the way that I think about this is this system is essentially pushing electrons towards that negative electrode. And it's negative because it's full of electrons. It's kind of like dripping with electrons. And so those electrons are given to the aluminium ions. Aluminium ions are just aluminium atoms that are missing electrons. So if they go over to the electrode here, they get given them back. The electrons are being pushed at them by the power supply unit. So the aluminium gains 3 electrons. What does it form when it gains 3 electrons, folks? Aluminium, right? And that's a half equation. So those of you who think you can't do half equations, that's all it is. Liquid aluminium ions are turning to liquid aluminium atoms. So we've made a metal from an aluminium ion found in a compound. So element from compound. And is that reduction or is it oxidation? Because it's gain of electrons, is it reduction or oxidation? Reduction, right. So reduction always happens at the negative electrode. Reduction, that's meant to say. And literally that's it. That's what's going on. And we'll see that in an exam question in a second, the one I just messed up. And the oxide ions are going to the positive electrode. But it's the chemistry that happens on the surface which is what's interesting to us. And again, this is where you get muddled, I would argue. So the oxide ions get there. And remember, this circuit is dragging electrons away from that electrode. So it's nicking the electrons off the oxide ions. And so the oxide ions are turning into the element oxygen. What's the formula of oxygen, the element? Tell that someone next to you. O2, right? It's diatomic, like all of these non-metals. O2, of course. And so what O2 means is that there's 2 oxygen atoms bonded to each other through a double covalent bond, right? We should know that from the bonding topic. So how many oxide ions must be required to make an oxygen molecule? An oxygen molecule, by the way, just to remind you, is that. How many oxide ions are required to make an oxygen molecule? Show me with fingers. Be nice. Okay, yeah, good, right, thank you. So 2 oxide ions are required to make an oxygen molecule. How many electrons is each oxide going to give away? Again, show me with fingers. Each one, how many is it going to give away? An oxide ion is 2 minus though, right? So an oxide ion's got 2 electrons more in its outer shell than an oxygen atom would have, of course, because it's 2 minus. So each one gives away 2 electrons. So how many in total would 2 oxide ions give away? So there's 2 of them times 2 is 4. That's all half equations are, folks. That's it. So those of you who are finding half equations a bit awkward, that's all you've got to do. So is this oxidation or reduction? Oxidation. And this would be the same if it was aluminium over here. I'm going to write a bunch of different ones that it could have been, right? So it could have been iron 2 ions. How many electrons would they gain? Shout it out. 2. And what are they going to form? Iron. It could have been over here chloride ions. What's it going to make? Shout it out. Chlorine, which is Cl2. How many chloride ions do you need? So how many electrons in total are being given away? Right. You can write half equations now. Right. That's it. That's literally what you've got to do. Right. Happy? Yeah, making sense. Yeah. Do you want to do another one? Are we all right? Hands up for one more. Okay, we'll do one more. So we'll do sodium ions. Just you, Darcy. Sodium ions. How many electrons is sodium going to gain here? Huh? So, Darcy. Yeah, you're going to say it. So say it. You're right. Yeah, well done. Good. It's 1 electron. Is that oxidation or reduction? It's reduction because it's gaining an electron. So if you see sodium being formed, it must be this reaction. And let's do, oh, it doesn't really matter, does it? Let's do bromide, the other one you might see. Bromide being oxidized here would give you Br2, 2 electrons are given away from 2 of those. Exactly the same every time, really easy. So, let's go back to the question I crossed out like an idiot before. Oxygen is produced at the positive electrode. We now know then, I haven't done this one, I deliberately left this one out, it's oxide 2 minus ions that are in aluminium oxide. So what's the half equation for that, please? I promise you, your mocks were not good with this. So can we do this? Or have I done this one? I've done it. So how many oxide ions are there?
2.
2. How many electrons are being given away?
4.
So easy. So easy. Right. But there's a little point about this. Look how many marks the next question is worth. The next question is worth 3 marks. This question comes up reasonably often. It's worth a heap of easy marks. If you think about how much of a grey boundary 3 marks is, this is the sort of thing you go, do you know what, actually, I might just listen for a second or two here. Again, before you start writing anything, let me explain it to you, because I think people find this hard. So let me draw to start with, and then we'll go from there. So if you've got electrolysis going on, this is not normally how they draw it. They try and draw it in a confusing way with 3 electrodes pointlessly. Right, so just thinking aloud. If you've got that going on, normally they draw a bunch of different cathodes and anodes just to confuse you, to make you think. But essentially, you've either got 1 or 2 or 3 electrodes. What they sometimes draw is this for aluminium oxide. They make that one of the electrodes and they stick that as the other electrode. Remember seeing this? It's just to confuse you. So they just, instead of having 1 cathode and 1 anode, they make the cathode the whole of the container. So this, the negative one, which is this one up here, this is the negative one. They've just made this the container, and they put 3 of the positive electrodes in the pot, right? Just to confuse you. There's nothing else different from what I've told you before. Now, in this is how they do aluminium oxide, and what you find is the aluminium ions and oxide ions are floating around in the cryolite. Where's the aluminium going to go? Is it going to go to the negative electrode or the positive electrode?
Negative.
Right, which is the bottom and the sides, right? And what's it going to do when it gets there? Get oxidized or reduced? It's going to get reduced, it's going to gain electrons. So on the surface of the bottom of the container there, aluminium ions gain electrons, become aluminium, and you tap that off with a little hole that's just here, right? But at the other electrode, folks, at the other electrode, so remember what I said at the start, can't concentrate if you're chatting. At the other electrode, the oxide ions are going there, and they're turning into oxygen, right? So O2 minus ions are turning into oxygen. Now, the little idea for this question that I just showed you is, well, why must the positive electrode be replaced? So if you get something like that, just go, well, I'm not, don't know maybe, but let's think, well, at least I know what's happening at the positive electrode. So oxygen being formed from O2 minus, right? If oxygen's being formed and you've got carbon electrodes, what happens is the carbon electrodes react with the oxygen. And that equation, I think just about everybody in here, with maybe 1 or 2 exceptions, could balance. We've got carbon reacting with oxygen to give carbon dioxide. Now, if the electrode's made of carbon, that electrode is being chomped away at, it's disappearing. So you need to replace it every so often. So I haven't written down what the 3 marks are for, though, but oxygen being produced from oxide ions, oxygen reacting with the carbon, so the carbon is the mass of the carbon, or the carbon electrode being sort of eaten up, being used up. Right, that'll do for now. We need to... Yeah, I like this question here actually. Right, so this is a nice question. Sorry, it's so small. Right, so this is an example. There's a couple of these I've got where the examiners are showing you something about that you've never seen before. Now, when this happens, folks, when this happens, don't be scared. If they show you something you've never seen before, go, right, it must be something from my specification, something I've been taught. All of your teachers will have covered all of the course, I promise you. So it must be something you've seen before. This must be something you've seen in this session, really. So you've got a power supply, you've got an electrode, you've got another electrode, but you've got it on a bit of paper there. That's a bit weird. You've never heard of probably copper chromate solution. Why would you have done? Copper chromate is green. You're told that up here. And then they turn on the power supply and you end up with this. We okay? We all right? Yeah, good. And you're told that this spot has split into two things. One of those things is blue, one of them is yellow, right? And you've all done Key Stage 3 art and probably know that if you mix blue and yellow, you get green, right? So that green thing up here has come as the copper chromate has come from something that was blue and something that was yellow. So you can kind of figure out what's going on. So what was the charge, do you reckon, of the blue ion? Show me with a plus or a minus. What was the charge of this stuff, given it's going towards the negative electrode? Right? And what was the charge of the yellow stuff that was in that compound? Yeah, fine. So copper chromate, you're told in the question, forms, look at 3 marks, right? 3 marks. Copper chromate's got 2+ copper ions, which you know are blue, because you all made copper sulfate, and this stuff you've never seen before called chromate ions. Explain the results. Well, copper 2+ ions are going to the negative electrode, they must be blue. Chromate ions must be yellow, because they're the other one, and they go into the positive electrode. And the green must be a mixture of the blue and the green together. Sorry, the blue and the yellow together, right? Does that kind of make sense? So that's that one there, and there's another one really similar to it here. In fact, I think it's exactly the same question. So, you know, they like this. We've got, instead of it being on chromatography paper, they've got it as a solution, and what you find is the solution splits. It's actually quite neat, it looks really cool, where you've got green solution, and it gradually becomes blue on this side, on the right-hand side, because this side is the negative one. Yellow over here, for exactly the same reason they've just discussed. So these kind of things, you can see electrolysis taking place for real in those kind of experiments. So let's have a look how the exam question goes, though. We've got to think about what happens at the electrode. So why would at the positive electrode, hang on, which one is it? Right, we're going to do the negative electrode one. So question 4.3, we'll come back to the other one. So 4.3 says, describe how the solid forms at the negative electrode. So again, this is copper chromate, remember? Copper 2+, and chromate, which you're told is CrO4 2-. Blue, yellow. Which one of those is going to go to the negative electrode? Cheer when I point to the right one. Right, so the blue one's going to the negative electrode when it gets there. Such enthusiasm, I like it. It's good. It is Friday afternoon after all, and I want to get onto the aqueous stuff, the stuff you're worried about. I'll do that really soon, but you might as well get the basics right first of all. So the copper ions go to the negative electrode. Right, that's going to get you a mark possibly, and they're blue, so you're going to see that blue colour. It starts off, remember, it starts off green and eventually goes blue, so the blue-coloured solution around the electrode, because I've written the wrong blooming thing. I've written it somewhere else, but anyway, the blue colour's going there around the electrode. This is wrong question, but you get the idea. What's going on, but then you have to say what's happening when it gets there, and hopefully now we've got the idea that it's the chemistry on the surface which is important, and you have to say the copper ions would be gaining 2 electrons, they'll be reduced, and copper atoms are forming, and you get the solid formed on the electrode. All right, so that's kind of what's going on. Okay, so the next thing we need to spend some time on, I feel like I'm rushing a tiny bit, but hopefully not, is what happens in aqueous solutions. And this is where And I'm sorry that I've left this the second half, where maybe your brains are frying a little bit. But without the basics, without the understanding of what's going on in molten compounds, you're going to maybe miss the obvious stuff. Right. So, electrolysis of aqueous solutions. What I might not get onto, though I'll share with you as questions, is voltaic cells, right? I might not get onto that. You might do that in class. I might do a little video on it as well at some point. But electrolysis of aqueous solutions is the thing that I think is one of the biggest battles, but almost guaranteed to come up in every paper every year. Many of you have done past paper ones and you've seen these questions appear lots of times. So aqueous just means dissolved in water. Forgive me if that's something you already knew. And I think you all know that water is H2O. But water isn't just water. Water in reality is 99.99999% water, which is H2O. But, and this is important for the acids topic really as well, and the equilibria topic as well, but actually there's an equilibrium reaction going on. It's a reversible reaction between water and something called hydrogen ions, which are, by the way, the ions that make things acidic, and hydroxide ions. If you don't know, this is called hydroxide ion, then it's probably worth learning. That's the ion that makes things alkaline. If you've got an exactly equal number of hydrogen and hydroxide ions, then it'll be neutral. And it's also worth remembering that the reverse of this reaction is neutralization. Little details that if you're going through this video, pause and add those details. That is an equilibrium reaction, and it lies very, 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 very far to the left. So I should draw maybe the first arrow, this arrow going very big that way, maybe the little one tiny that way. But there are, importantly, a small number of hydrogen ions and hydroxide ions in solution. For those of you who want to know, a little bit of random stuff, the concentration of hydrogen ions and hydroxide ion solutions we know is 1 times 10 to the minus 7 moles per decimeter cubed. And that number 7 there is why the pH of water is equal to 7. Little aside for those of you who think about doing chemistry next year. Anyway, but those ions are charged, like the sodium ions, like the chloride ions, like the aluminium ions, like all the stuff we've talked about before. So they will also be in the pot when you turn on the electrolysis, you turn on the power supply unit. They could get involved. They're going to move around as well. So if you've got sodium chloride, for example, being electrolyzed, you will have sodium ions in solution, and you'll have chloride ions in solution. But you'll also, if it's in water, and only if it's in water, have hydrogen ions in solution, small number, and hydroxide ions in solution. So, which ions are going to go to the negative electrode? I'm going to point and you're going to go, yes, if you think it's going to go to the negative electrode. So, this one? This one?
Yes.
This one? This one?
Yes.
Right. So, and there you go, you've all just answered that perfectly, but in an exam I can tell you that most people think only one of those two things goes there. They both go to the negative electrode, the both of them. And it's what happens on the surface which is what's interesting. It's which one of them reacts, which one of them gets reduced, which one of them gets what we call discharged, stops being charged. We'll talk about what happens in a minute. The other two, of course, go to the other electrode, and we'll talk about that in a second. Right, so when we get there, reduction can take place, and over here, oxidation can take place. So we've got two options on both sides, and you ideally would know, if you want to push those 8s and 9s, which is why you're here, we need to know which one gets discharged, and a little bit about why. We'll do it properly in year 13, sort of properly in year 13, but we'll do a little bit on why now. So either the sodium gets reduced, and we all now know how to write half equations, or hydrogen ions get reduced. What's the elemental form of hydrogen, folks? Tell each other. Good, it's diatomic, so how many hydrogen ions would be needed? How many electrons in total then do they need? 2. So that's the half equation so you can write half equations now. That's the half equation for reduction of hydrogen. So one of those two things can happen, but not both. You're going to get one or the other. And the oxidation is either going to be chloride ions that are oxidized to give Cl2, and we know how to write that half equation. And then this is the one that's quite hard you're going to have to learn, and I'm not going to teach you, apart from telling you it now, I'm not going to teach you how to practice it now. Just try and learn this equation if you haven't already. Certainly know that hydroxides are oxidized to give oxygen. If you can learn to balance and write down that equation, marvellous. But the key thing is that you've got oxygen being produced there from hydroxide. So they're the two possible reactions at the positive electrode. So I've gone sort of fairly complicated, and now I'm going to go easy again, and I'm going to step it up a little bit again after that. So neg electrode, pos electrode, and then compound over here. So at the negative electrode, the only answers you're ever going to get are H2 or copper, probably, possibly silver. Okay, now this is an aqueous, remember, not liquid, aqueous, dissolved in water when hydrogen ions are present. They're your only possible answers. If you're writing anything other than those, you're wrong. The reason that in most cases you get hydrogen formed is that the other element, sodium or lithium or magnesium or zinc or all of the other ones you might have seen in class, potassium, magnesium, whatever else, whichever ones I haven't said, they're all more reactive than hydrogen. If you look at the reactivity series, all of the elements except for copper and silver are more reactive than hydrogen. Being reactive, all being reactive means is that they like being ions. And they like being ions more than hydrogen likes being ions. So hydrogen stays as the ion. So the more reactive element, the sodium or the lithium or magnesium or zinc, stays as the ion. And so it must be that the hydrogen ions are reduced to make H2. Right? So it's always going to be hydrogen or copper or silver. Silver and copper, Ag and Cu, are less reactive than hydrogen. So given a choice, they will be reduced first, and you'll see the copper forming on the surface of the electrode. It makes a brown solid or a silver solid or sort of blacky silver solid on the surface of the electrode. But it's nearly always hydrogen here. The positive electrode, you always go, and you don't have to explain the positive electrode at all, but the positive electrode is always a halogen, so Cl2 or Br2 or I2. And if a halide, chloride, bromide or iodide are present, then they will be discharged. They will go from chloride into chlorine, bromide into bromine, iodide into iodine, just because, and that's not explained why at GCSE. You just need to know it. The alternative, as we said, is that hydroxide is oxidized. So if you haven't got a chloride, say you've got sulfate or nitrate, and they're the most common ones, it's going to be this alternative reaction that happens. Right? So the only two things that can happen. So if I tell you a compound, we'll start with sodium chloride, the one we just talked about, AQ. What's going to form at the negative electrode? Hydrogen, copper or silver? 3, 2, 1. Hydrogen, because it can't be copper or silver because it ain't there. And you can write the half equation if you want to. What's going to form at the positive electrode? 3, 2, 1. Right. Whoops. Cl2. What about if I had copper bromide AQ? Not even sure how soluble that is, but whatever. So what's going to form at the negative electrode? 3, 2, 1. Right. Easy, isn't it? What's going to form at the positive electrode? 3, 2, 1. Bromine. What about if I had zinc nitrate, stuff you've never seen electrolysis on before? You can now do these. What's going to form at the negative electrode? 3, 2, 1. Is it copper, silver or hydrogen? What's going to form there? 3, 2, 1. Hydrogen, because it can't be anything else. And the answer to why, by the way, and I'm not going to write this down because we're running out of time, is because in this case sodium and in this case zinc, they're more reactive than hydrogen, so stay as the ions, whereas copper is less reactive than hydrogen, so it is discharged. Discharged just means turned from being a charged substance into a neutral substance. Okay, with me? Yeah. What about the positive electrode? What's going to be formed there? In 3, 2, 1. Oxygen. So that would be our 2, by the way, oxygen there. And hopefully you'll learn that half equation. That half equation's worth a couple of marks. Okay. So let's have a look at some exam questions on that now. So here we go, some easy exam questions. Complete the half equation. What's missing on that line, please? Everyone shout out. 3. Easy, innit? Cryolite has got sodium ions as well as the aluminium ions, right? Think about what I just taught you. Why is sodium not a product of the electrolysis, right? So this is a question which is not in the spec, but I've just taught you the reason, even though it's with a different example. What's the answer? Discuss it. Discuss. To do with reactivity, isn't it? It must be. Okay, good. Thank you. Stop. So I'll ask you directly then, which one is the more reactive element? Sodium or aluminium? 3, 2, 1. Sodium. So sodium is not a product because it's more reactive than aluminium. Really good. Right, 4 marks for this. Did I even? I think I might have printed out the mark scheme for this one. 4 marks for this one. Hydrogen's produced at the negative electrode, oxygen produced at the positive electrode. Right, so 4 marks for what I just told you. Let's see if we can figure out how we could possibly get 4 marks for this. Let's do it together. You have a little chat and we'll do it together in a second. Right. Okay, good. I'll pause it and I'll ask a few of you, then I'll record it again.
Since it's an aqueous solution, that means there's going to be hydrogen ions and hydroxide ions in the solution as well as the other 2 ions.
One thing at a time. We have got in there, and this is the second point, marking point, the hydrogen and hydroxide ions present. How many of you said that? Nod or shake your head. Right? Where do they come from? Where do they come from? What's broken apart to form H plus and OH minus? Yeah, so H2O breaks apart, breaks up, what's the word that actually says? We just said water molecules break up to form H plus and OH minus. And then what happens to the OH minus ions when they get to that electrode? Well, what you'd say is which electrode they go to. It doesn't tell you in the question that they go to the positive electrode. Believe it or not, this is easy because you know this actually. I've just told you. You telling me the answers back a minute ago. OH goes to positive electrode. It's worth a mark. What happens to it when it gets there? Does it get oxidized or reduced? 3, 2, 1. Yeah. And gets oxidized. That's literally it. That's so easy. But actually, when I asked you, even having just taught you, getting 4 marks there would have been tough. That was then a fairly brief but hopefully useful review of electrolysis of aluminium oxide to make aluminium and oxygen using electrolysis and discussion around that. It was a review of generally electrolysis of molten compounds and then aqueous compounds. But there's a lot to go there. I'm not stopping. I'm going to go for 3-4 minutes and then we'll stop at 25 past. Okay. So what I want to do is I'm not going to have time now to go through these, but I want to show you a couple of tiny bits that I really encourage you to go and spend a minute or 2 on just before we're done. Just before you know over Easter or something. One is around hydrogen fuel cells and about rechargeable cells. So you don't need to be the world's expert on hydrogen fuel cells. They're quite complicated. All you really need to know is a way of making electricity from the reaction between hydrogen and oxygen to give water. So we've got an exothermic reaction going on. We use that to generate electricity. And you might need to talk about some advantages and disadvantages. I'm going to share this. I've scanned all these questions. I'm going to put them and the mark schemes on Google Classrooms straight after the session. So have a look at that. Rechargeable cells are also covered. Make sure you're aware of the key advantages and disadvantages. Don't get hung up on the chemistry. The chemistry is really hard, really complicated. But make sure you know the environmental advantages of just making water rather than, say, carbon dioxide. But be aware that you've got toxic chemicals in them, which might make it problematic. So focus on the environmental issues and stuff like that there. Ideally, learn the reactions if you can, but that's only ever good. Look how many marks it's worth. It's worth 1 mark, right? So don't get hung up on the chemistry because it's a tiny bit if you find that tough. The other thing I haven't done at all is talk about voltaic cells, right? These cells where you put 2 bits of metal, 2 different metals like nickel and copper, or zinc and copper, silver and zinc, whatever, two different metals into some sort of solution. If you do that, you get a voltage. Now, the only thing you really need to know here is the bigger the difference in reactivity of those 2 metals, the bigger the voltage, right? And that's kind of what you've got to do. And it's quantitative. You can start to piece it together. So I'd encourage you to have a look at this question as well. And this is a bit of a beast because it's a 6 marker. It tells you you've got to work out an experiment. If you're asked to plan an experiment, make sure you talk about keeping things like everything controlled that might affect the experiment, repeating experiments, how you measure stuff, what you measure stuff with, making sure that you, as I said about controls, making sure you say how you control stuff, and then obviously just talk through what exactly you would do and how you'd interpret the results, what data you're going to measure, and all of that kind of stuff, right? But so even if you get stuck on something as complicated as that, you can at least pick up relatively easy marks. Okay, so apologies for not covering any more than electrolysis and stuff, but I hope that's the best I can do in an hour. Hopefully that was useful. I'll walk you out in a sec.